Okay. Hi everyone. I'm Haoming Wang from University of Pittsburgh, and it's my pleasure to present our work. Never start from scratch. Expediting on-device LLM personalization via explainable model selection. And this is a joint work with Boyuan, Yang, Xiangyu, and my advisor, Dr. Wei Gao. And with the growing capability of large language models, we are seeing a wide range of intelligent applications to emerge. And to better meet the unique needs of individual mobile users, LLM personalization is becoming increasingly important. And this is often achieved by fine-tuning the model with the user's personal data. For example, a personalized LLM can serve as an assistant adapted to the user's preference in different scenarios. Or it could also be a tutor that are personalized for the students' different learning style. And a straightforward way to personalize an LLM is to upload the user data from the mobile device to the cloud server and fine-tuning the model on the cloud server. However, doing so will expose the sensitive data to the cloud, which may lead to privacy leakage. So instead, a more privacy-preserving method is to directly perform the fine-tuning on the user device. However, this approach faces some challenges due to the limited computing power and the insufficient personal data. And these two challenges cannot be addressed by simple existing methods. First, regarding the limited computing power, we can use some efficient fine-tuning method to reduce the computing cost. However, such reduction is not significant enough because they still need to back progress through the entire model. So, in our experiment, even fine-tuning a 0.5B model for one training step on a flagship smartphone, it will also need 1 second even with the efficient fine-tuning method. And second, for the insufficient personal data, to avoid bias or overfitting, we usually need thousands of data samples to fine-tune the data. However, for a single user, it will take a long time to accumulate this many data. Continuous learning can allow the new data to arrive during fine-tuning. However, these algorithms are usually too expensive for mobile devices. So in our paper, we propose a fundamentally different method. Instead of starting from scratch, which means starting the fine-tuning from a general pre-trained base model, we choose to start from an existing personalized model. We begin by the assumption that after each user finishes the personalization, the resulting personalized model, which are PLM in this figure, are cached on the cloud server. And to support future users, we propose a new technique that can generate some explanation about how the models are fine-tuned. These explanations are designed to be highly compact, so the communication cost of transmitting them to the user's device is minimal. And when a new user initiates the personalization, instead of starting from a base model, it first downloads the explanation from the server and compare them locally with its personal data to identify the most relevant PLM. And finally, the user device downloads the selected model and continue fine-tuning from this personalized starting point. So in our framework, the effectiveness depends on the accurate model selection. So to ensure high accuracy, we require that the explanation should meet these two requirements. The first is that to ensure the user's trust in our framework, the explanation should clearly describe how the models are fine-tuned in natural language. And the second is to support model selection. The explanation also needs a numerical metric to measure the difference between models. So based on these two requirements, we designed the format of explanation by breaking down the language style of a personalized model into multiple orthogonal dimensions. And so in this figure, each dimension comes along with a natural language description and a numerical value to indicate the degree of personalization in that dimension. So to achieve model selection with explainability, we propose Expert, which means explainable personalized tuning. And here is an overview of Expert. For each PLM, we first compare its output with that of a base model. And with the help of another summarization model, we can map this difference in the distributions into an embedding vector. And to further interpret this embedding vector, based on the linear representation hypothesis, we can further decompose this vector by a set of orthogonal subvectors. And so in this figure, each subvector comes along with a natural language description, and the coefficient in this decomposition can serve as the numerical metric for the explanation. And this set of subvectors are also proposed by the same summarization model. And finally, the user device can download the explanation to local and compare them with that of the personal data to find the most similar one. And in the following slide, I will explain some technical details of these three main steps in Expert. The first step is to map the difference to embedding space. And here is a more detailed flow of this process. First, we prompt both the model with the same set of samples and to generate some personalized and unpersonalized output. And then we employ a summarization model to summarize the difference between these two distributions. And instead of directly using the model's final output, we choose to extract the hidden state, which means the embedding before the output layer. So in this way, the difference between these two models can be quantified. For the instruction, we prompt model to summarize the difference into one adjective, so that in this way, the difference is captured by the embedding of the first token. And we repeat it for multiple times and average the resulting embedding to get a stable estimation vector. And the second step is to decompose the embedding, and it consists of three parts. First, we need to propose some candidate for the description. In the previous step, we stopped by the embedding space, and we can further let the model finish its generation to propose a list of possible keywords with its possibilities. And then we need to compute the embedding for every keyword. A straightforward way is to first ask the summarization model to generate some synthetic text that can reflect the style of that candidate. And then we can repeat step 1 to convert the changes in the text style into an embedding. However, doing so is very inefficient because we need to run many times of inference for every keyword. And we noticed that in this entire flow, the embedding vector comes entirely from the summarization model's internal knowledge. So instead of delivering the internal knowledge via some intermediate text, we can go one step further, which means we directly prompt the model to generate a subvector based on the keyword. So to ensure accurate generation, we need to carefully craft the instruction prompt. So we do offline prompt tuning, which means we treat the instruction prompt as trainable parameters, and the embedding generated by the original inefficient method can serve as the ground truth of this prompt tuning. And once the prompt is optimized, we can use it online to efficiently generate embedding. And we just repeated step 2 to compute the embedding for different candidates and until the decomposition error is small enough. Okay, the second step is on-device model selection. After downloading the explanation of PLM, the user device also needs to compute the explanation for its personal data. This can also be done by repeat the step 1 to convert the personal data into an embedding so that we can further use the same set of subvector to decompose this vector. And however, in step 1, we need to run an summarization model on the mobile device, which may be too large to fit in the memory of the mobile devices. So we choose to partition the model by layer, which means we run one layer at a time, and the output of the previous layer is cached in the memory and passed to the next layer. Since in this task, we only need to get the embedding of the first generated token, so each layer only needs to be loaded and executed for one time. So the cost of switching between layers is minimal. And in some scenarios, even the best matching PLM still largely misaligned with the personal data as shown in the figure. So in this scenario, we will try to merge multiple models to better resemble the personal data. So to do this, we first try to combine the explanation of multiple PLM to get an explanation that is close to that of the personal data. And the coefficient in the combination, which is alpha and beta in the figure, can help to get the model merging as shown in the formula below. So after this, we can start the fine-tuning from this merged model. And for implementation, a technical issue is that most of the existing framework for mobile deep learning doesn't support the fine-tuning LLM on smartphone. So to implement Expert, we divide the fine-tuning process into two phases. First, in the offline phase, we use the server to pre-convert the format of the model from Hugging Face to Onyx and generate some training artifacts. In the online phase, the smartphone first downloads the selected model and wrap it into an Android app. So the app can use Onyx Java API to launch the fine-tuning as a background service. In the evaluation, we fine-tune a base model to a personalized model with two datasets with diverse language styles. For the synthetic data, we prompt GPT-4 to generate text with specific data and with specific language style, and the language style are characterized by these three dimensions as shown in the left table. And to better simulate the real-world scenario, we also construct the real-world dataset by combining three text corpora with multiple language styles as shown in the right table. And we conduct experiment on three different smartphone models with varying hardware resources and run LLM of different sizes according to the smartphone's capacity. And for evaluation, we also compare Expert with starting from scratch and three baseline selection methods. The first baseline is exhaustive search, which means just basically evaluate every PLM output with the personal data. And the other two baselines frame the model selection as a hyperparameter to be optimized. So we first compare Expert with fine-tuning from scratch. And to simulate the different levels of similarity between the PLM and the personal data, we make some default sample, which means samples without any language style into the fine-tuning data of PLM. So in this way, we can measure the similarity by the percentage of stylized data in the fine-tuning data of LLM. In the right figure, we can find that Expert can achieve high selection accuracy when the similarity is larger than 70%. And thanks to this high accuracy, Expert can significantly reduce the computing cost and improve the data efficiency. From the right figure, we can find that the model trained by expert have almost identical performance with that of training from scratch. That means expert didn't sacrifice any model performance to reduce the fine-tuning cost. And then we compare expert with three baseline selection methods. And from these three figures, we can clearly see a difference in the scalability. For the baseline, the selection cost almost linearly increased with the number of models. So this makes them impractical when there are too many models to select. And for expert, it can always retain a consistently low level of selection cost, because in expert, we only need to download the explanation and one selected model. And our model selection based on assumption that is closer distance in the decomposition coefficient correspond to similar style of personalization. So to verify this, we synthetic data with varying style of personalization, and from the right figure, we can find there is always a consistency between the distance of coefficient and the difference in the personalization levels. And finally, we verify the effectiveness of on-device model merging. And in this scenario, the personal data consists of text from multiple styles. So in this case, none of these existing model is a perfect match of the personal data. And from the right figure, we can find that expert model merging can always achieve some extra reduction in the fine-tuning cost. So in summary, we propose expert method that can accelerate on-device LLM personalization by starting from a well-matched model. And the explainability of expert can ensure the trustworthy and accurate selection. And for more information, you can check the more details in our live website or the GitHub repo. Okay, thank you.
Let's thank the speaker for an amazing talk. And again, I just want to highlight that they have shared the code, so we can build on top of it. So yeah, questions.
Okay, great work. This is Lemi from Hong Kong PolyU, and my question is that how you initialize a list of PLMs, and what are the selection metrics when you initialize them?
You mean how do we first get a pool of PLM to select?
Yeah.
So that means we can start by, for example, in Hugging Face, there are many open source models that fine-tuned on different data. We can use this set of models as the initialization of the pool of PLM. And for the system, when the new user continue to join our system, the pool of PLM will continually extend, so that will benefit the future users.
Okay, I see. And another question is that, so when the personalized data on the device is less similar than the existing PLMs, you choose to merge the two PLMs.
Yeah.
And my question is that why not consider adding one more new PLMs on the server side? Why not choose? Why choose to merge? Yeah.
For example, we have on the server, we only have a model that is fine-tuned to generate, for example, concise data, and another PLM that is fine-tuned for generate, for example, formal data. But the user need is to, I want to get a model can generate data that is both concise and formal, and there is not. We can't find any existing PLM in the pool, so we can try to merge multiple models to combine the aspect of personalization.
Okay, I see. Okay. Thank you very much.
Okay.
Thank you for your presentation. This is Jing Can from Hong Kong UST. So to my understanding, you had an assumption that there are many personalized LLMs that is from previous users. And my question is, under what scenario or in what applications do we have such personalized LLMs that is transferred to the cloud servers?
I think first similar to my previous response. In the area of LLM, there are many open source models can serve as the existing or already personalized model as the initialization for our system. And I think, only sharing the model parameter doesn't violate the privacy, so the users are willing to share their model to the cloud server.
Okay, thank you.
Hi, thank you for your presentation. I'm Jing Li from Michigan State University. I have a confusion. When you motivate us to use like personalized LLM on device, you mentioned it's about like a great privacy benefit. Yet, your method used a cached PLM on the server, which seems a little bit on the other side of the privacy when the personalized data is on the server, which you assume is not like encrypted or private. So how do you address your privacy concern after your method? That was
we
already
usually consider that only sharing the model parameter, such as factor learning, won't violate the privacy. So maybe only if we need to share the raw data, then it will definitely violate privacy. But if I only need to share the parameter, I think that is okay in most scenarios.
Yeah, hopefully.
Okay.
All right, we'll take the rest of the questions offline. Thanks again for a great talk.
Okay.
And we'll move on to our last speaker of the day,